Continuing our look at slope fields, this is a Geometry Sketchpad sketch which basically allows you to paint on a slope field. What happens is, as I move the point around, it's going to take the coordinates of the point, plug them into a sample slope field, and plot the appropriate tangent line. So as I move this around, we keep getting these segments, tangent segments, being dropped down. And what you end up seeing after a little while is basically a family of hyperbolas. It ends up being a rather simple differential equation, something like y prime equals x over y is this differential equation, which will lead to a slope field like this. So that could be a graphical solution to a differential equation. Then we have initial condition, which we would just put through some of these dashes. Here is the differential equation y prime is negative x over y, and for this one we see it's a family of circles. If we separated variables, we would easily get x squared plus y squared equals c. As far as getting a more accurate representation using a slope field, well, if we want to make the spacing a little bit tighter, down to maybe 0.25, they're a lot closer together. Of course, I've got to drag the field around to where I want it to be. I can't expand that, but that allows me to get a more accurate representation of what things look like. If I make these segments a little shorter, it's not quite as busy. So that's ways to use the technology to get a better and better solution for a slope field. And certainly there are plenty of web pages you can find where you type in the differential equation, initial conditions, and it gives you a very accurate slope field. One application for these you see is in predator-prey relationships. And so the idea again is you have a differential equation which, in this case, x squared minus 4 over x plus y, which tells you how two species interplay. And so this seems, with this initial condition, it spirals into this particular solution of populations. If I move the initial condition slightly, though, things can change dramatically. So clearly there's some area in here where if the populations change in some way, some minor way, a fundamental change occurs in the ecosystem. Because if I come over this way, eventually I will keep spiraling into the same area. So that's relatively stable up here. Now looking at some more examples creating slope fields, here we have the differential equation dy dx equals x squared minus y. Relatively simple, and yet it's not separable, so we can't do it using separation of variables. Some things to look for when you make slope fields is where flat dashes are positive slopes and negative slopes. Flat dashes are where the derivative is 0, so I set it equal to 0. I'll have flat dashes wherever y equals x squared, and so that will be places like here, here, and here. Picking at other spots, say when 1 comma 0, of 1 comma 0 I got 1 squared minus 0, so that's a slope of 1, 45 degrees. 2 comma 0 will be a slope of 4. Negative 1, 0 is still a slope of positive 1 because I'm squaring it. And then over here, negative 2 comma 0 is a slope of 4. Here would be the finished product. So the main thing is to get the flat dashes right, get the positive looking positive, negative looking negative, though it's okay if the slope of negative 2 here isn't quite the same as the slope of positive 2 somewhere else. It's not that crucial. Another example, we have dy dx is x minus 2y with an initial condition of 2 comma 1, this point in green. You have flat dashes when y is equal to half x if you set this equal to 0. So with these spots, and then just plugging in all these points, we can get this differential equation, or slope field, excuse me, for the differential equation. Either the blue or the yellow would probably be something about what the solution looks like. Of course, more advanced technology can give you a much better idea of which one would be the one which would truly go through 2 comma 1. So looking ahead at more examples now from the textbook, what we see is a few things I want to point out. Here we have a differential equation, half x minus 1. It's linear, so if we integrate it, we would get a parabola, and you can see this is a family of parabolas. Flat dashes when x is 2. No dependence upon y. There's no y here in the differential equation, so as I move vertically, there's no change. Over here, no y dependence either, so vertical movement doesn't change anything. This is a quadratic, so if I integrate it, I get a cubic, and these look like cubics. And you can see flat dashes at plus or minus 1. Over here is cosine, so it's sinusoidal, and of course, the differential equation looks sinusoidal as well. Again, no y dependence for either of these. When I get down to this one over here, now I've got a differential equation which is odd. The x is an odd piece, the e to the negative 0.2x squared is even, together that's odd, and the solution, the slope field, looks actually even. And it turns out that if you look at a odd differential equation, it's an even slope field, symmetric about the y-axis, and vice versa. Even differential equation, you're going to look like an odd slope field. So I also see no y dependence. I see that symmetry about the y-axis. I see flat dashes when x is 0. Here I finally have some y dependence, so I have flat dashes when y is 6 and when x is 0, and as I move up and down things change. Plenty of stuff changing up and down here. We got a lot of symmetry though amongst the 4 quadrants. Here's my odd differential equation, so I'm an even slope field, and of course this is just families of parabolas. This is family of circles as I showed on the previous page. Here we have flat dashes when y is 4, no x dependence, so as I move left and right nothing changes. Over here I've got flat dashes at x equals 0, y is 4. So it's important to look at these things if you're going to match stuff up. Down over here the idea is to go from the words, the differential equation in words, to a differential equation here in mathematical notation, and then from there try to match it up with an actual slope field. And so we have flat dashes when y is 4, flat dashes when y is 0 and 4, that's our logistic growth here. Flat dashes when x is 4, that's linear becomes parabolic. And finally this last one where it's dy dx equals ky squared, we have this y dependence but no x dependence again.